Hey guys, this is Mrs. Harbin and this is Algebra 2. We are looking at section 3.3, solving problems with systems. So we've learned how to solve systems by graphing and substitution and the elimination method, and now we're going to look at why we actually need these or how we might use them. Just a reminder that everything we do is going along with this dominion mandate, that we are supposed to have dominion over the earth. We are supposed to take care of the earth, love people, as part of God's creation. And so we're using systems to solve problems that can benefit other people. And God's given us this ability to think rationally and to reason through problems. And systems math is just a way that we can solve problems. Some things are pretty easy and we can solve them with just one variable, but a lot of times we're going to have problems involving multiple issues, multiple variables, and we'll need systems to help us solve those problems. Our life application for this unit is this. The student will know that Jesus is constant and he alone is the way, the truth, and the life. Jesus is not a variable. He is a constant in our life, and he's not a problem that we're going to have to solve depending on the context. Jesus is the same yesterday, today, and tomorrow. So not a variable. But in math, so many things are a variable, and we do need to be able to think about them logically and reason through them. Our lesson objective for today is this. You, the student, will solve word problems using systems of equations. Now, so many times students say, oh, I hate word problems. But really, word problems are real math. We do book problems, yes, and the book problems help us to learn the steps and solidify the process. But we're not actually solving real problems. Word problems give you actual problems that you might see when you have a job someday and you're working a career. And so you're now taking the steps that you've learned and you're applying those to real problems. And for me, it's like, hey, this is how you use this math. It's not just some random numbers that we threw in a math book and said, memorize these steps. There is actually a use for that, for this math that we're learning. And that's why word problems to me are so exciting, because you get to see what this is for. So don't look at word problems as hard problems. Look at word problems as, okay, I've learned these steps, I've mastered, I know how to do substitution, graphing, and elimination. Now let me actually tackle some problems where I have to think on how to apply these steps. So let's look through some examples together. You're not going to learn anything new about solving systems today. We're going to be using the steps that we've learned in the previous lessons and tackle some real problems and how we can apply these steps. Most of the problems that we're going to see today are mixture, motion, or digit problems. That's not the only place that you'll see systems of equations, but just for the sake of what we're doing, we're going to keep it to those three fields of study. So let's first take a look at a digit problem. So in example 1, we want to find two numbers whose sum is 23 and whose difference is negative 81. So two numbers, we've got two variables whose sum when added will equal 23, but when subtracted will equal negative 81. So first of all, is this even possible? Well, you might be thinking, of course it is. You wouldn't be asking me if it weren't possible. But yes, it is. So a couple of things. If I'm going to get a negative 81, that makes me think that one of my numbers must be negative. In fact, I'm getting a large difference of negative 81. So maybe one of my numbers is quite large and one of my numbers is a little bit smaller. If we tried out some numbers, numbers that I know add up to 23, 20, and 3, but the difference of that is only 17. So 20, 22, and 1, or 23 and 0, again, the biggest difference I can get is 23 there. So one of these numbers must be negative. Just thinking about some logical answers here that would fit the bill of my description here. So let's set this up using variables. We're going to let x equal our first number, and we're going to let y equal the second number. We're going to do two variables here. That's what when we solve systems of equations, we're trying to solve for two variables. And then I'm going to write equations based on what I know. Remember that when we solve problems, we want to start with what do I know. So I know that these two numbers, when added, equal 23. So I'm going to write this x plus y equals 23. Two numbers whose sum is 23. Sum is plus, is an equal sign. There's my first equation. And I know that the difference between these numbers is negative 81. So I'm going to write a difference equation. X minus y equals negative 81. And now I've got a system of equations that we could solve. We could solve this by graphing, we could solve this by elimination, we could solve this by substitution. Just taking a look at it, I would say graphing is probably not going to work so well because I don't want to make a graph that goes to negative 81. I could do substitution, Or when I look at it right away, I notice that my y terms, I have a positive y and a negative y. If I use elimination, these y terms will eliminate right away. So I could use elimination. In fact, that's exactly what I'm going to do. When I combine these two equations, my y's are eliminated, and I end up with 2x equals negative 58. Solving for x, I find out that x is negative 29. And if you remember what I was thinking beforehand, one of these numbers must be negative. There's a negative number right there. Once I know what my x is, I can substitute it back into one of my original equations to find out what y is. So I'm going to substitute it into the first one. And I find out that y is 52. If you remember what I said beforehand, one of my numbers must be pretty big to get a difference of negative 81. 52 is a pretty big number there. So my numbers are 29, negative 29, and 52. If I plug both of those back into my two equations, x plus y equals 23, and x minus y equals negative 81, I'll find that both of those statements are true. So this is a solution for both of these equations. So that was an example of a digit problem. We can also use systems of equations to solve problems involving finances. In fact, the financial world probably uses systems of equations more than maybe any other field. I mentioned that the other day. We have this formula for simple interest. PRT equals I, or I equals PRT. And you've got I is your interest that you're gaining, P is your principal, R is the rate of interest, and T is the time. So if you're not sure how banking works or money works, I've mentioned this before, when you deposit money into a bank, say your savings account, the initial amount that you deposit is called your principal. The banks will pay you a certain amount of interest to be able to use that money at their discretion to loan to other people, what have you, until you're ready to withdraw it. So interest rates range from, 0.5% to like 1.15% on a traditional savings account. I'm not sure about the 0.5%, but it gets pretty low. Okay, so not a whole lot of interest. And then time is how long you're keeping that money in the bank. The longer that you keep your money in the bank, the more interest that you are gaining. And that's what this capital I stands for. So if you put $100 in the bank and you're getting paid, 1% interest each year, then at the end of that year, you've made $1. Well, it doesn't seem like a whole lot, but that can compound over time, and you're probably going to have more than just $100 in the bank. Anyway, that's where this formula comes from. This is what it is. So the rate and time are typically given in years, and I mentioned that earlier, 1% per year is what we kind of mentioned. This example comes from page 118 of your book if you wanted to take a look at it while we are going through it. So we're told the different variables here, all right? The example is that Mr. Perry has invested a total of $10,000 in 2 stocks, okay? So we know our initial amount that he is investing. AmeriCorps returned 8%, while Bancorp returned 10%. There's our interest rates. How much did he invest in each stock if his total return last year was $850? So we know his capital I, his total return. We're going to let X represent the amount that he invested in AmeriCorps and Y represent the amount he invested in Bancorp. And we don't actually know the principal that he put in AmeriCorps. We know his total principal that he invested was $10,000. This is going to start to resemble those mixture problems that we did earlier this year, guys. Hopefully you've mastered this by now. So we're going to call AmeriCorps X, and Bancorp we're going to call Y. We know the interest amount. We know AmeriCorps was 8%, represented as a decimal, 0.8, and Bancorp was 10%, represented as a decimal as 0.10. We know the time for both of these is 1. And in order to determine the gain or the total interest in each, if you remember, I equals PRT. So we're going to take these 3 things here, PRT, and write that as one expression. So we get 0.808x. And same thing down here. We're going to take these 3 and represent that as 0.1y. We know that the total amount of interest that he gains is $850. That's the total amount of interest. So the interest from Bank 1 and the interest from Bank 2 will, or account 1 and account 2 will equal that total interest. And we know that X plus Y equaled $10,000. And we know that 0.8x plus 0.1y equals $815. We now have ourselves a system of equations. Again, we could solve this by graphing, we could solve it by substitution, or solve it by elimination. Graphing is probably not reasonable with that $10,000 there. So let's go ahead and solve it using some, they don't show the steps on this slide. I just realized we're going to solve this using elimination. And when we eliminate those y's, what we're going to find out is that x is equal to 7,500. You could have also done this via substitution, taken x is equal to 10,000 minus y. But by elimination, we find out that x is equal to 7,500. When we plug that back in, we find out that y is equal to 2,500. That tells us he invested $7,500 in AmeriCorps and $2,500 in BankCorps. If you need to see the steps for that worked out, you can see that on page 118. I'm not going to write all those steps here in elimination. But elimination is a method that was used to determine that x equals 7,500. All right, let's take a look now. We've done a digit problem. We have done another digit problem involving money. Let's take a look at a motion problem here. All right, we've got example 3, which is on page 119. Two buses, 412 miles apart, head toward each other. One bus travels 3 miles an hour slower than the other, and they meet in 4 hours. What is the average speed of each bus? Now, for this particular problem, you're going to need to remember that distance equals rate times time. It's another formula you need to know. Distance equals rate times time. Think about it this way. If I know my rate is 60 miles an hour and I drive for 1 hour, my distance, 60 miles. So we use distance equals rate times time frequently in everyday driving. Even though we may not actually think D equals RT, we're writing down the equation. We are using that to figure out total distance driven and our speed. All right, so we've got two different buses. We know that the total distance that they are apart from each other is 412 miles apart. And that should be a 4. It didn't look like a 4. And we've got a slow bus over here, or a slow vehicle over here, and a fast vehicle over here. So let's fill in our chart with what we know. Okay, for our variable, I use an S. You'll see in the chart in your book they use RS. It just means the rate of the slower bus, but that's one variable. And then we have RF for the rate of the faster bus. I just used F up here in my picture. You could use F or you could use what they use. Our time is 4 hours. We know that they meet in 4 hours, so they each drove for 4 hours, and our distance equals rate times time. So we're going to write an expression for our distance for both vehicles here. We have 4 times RS and 4 times RF, or 4S and 4F. We know that the total distance, if we add their distances together, is 412 miles. We don't know how much each one of them drove, but we know they drove a total of 412 miles. We also know that it tells us one travels 3 miles an hour slower. 3 miles an hour slower. So we also know that the rate of the slower bus is whatever the rate of the faster bus is minus 3. That's something else that we know from that piece of information. Okay, we can write that up at the top here. And those are the two equations that we now have. Now that we have two, we can do a little system of equations. This is already solved for RS, so it looks like the best method here might be substitution. So wherever I see RS, I'm going to plug in that RF minus 3. That will look like 4 times the rate of the faster vehicle. I'm just going to put an F minus 3 here. Plus 4 times the rate of the slower vehicle equals 412. Then we're going to use the distributive property to get rid of those parentheses, combine like terms. And when we do so, we find out that the rate of the faster vehicle is 53. Remember, we were told at the beginning that the rate of the slower vehicle is just the fast vehicle minus 3. So the rate of the slower vehicle is 50, and that is what we were looking for, the speed of each bus. Faster bus traveled at 53, and the slower bus traveled at 50 miles per hour. When doing problems that involve traveling upstream or against a current or into a headwind, make sure that you're paying attention to those positive and negative rates. If you guys have any questions, be sure